If you are looking for a way to understand what a force really is, or if you are feeling lost among all the formulas involved, this video is for you. I'm going to show you a super quick technique with almost no prerequisites to solve any exercise involving the equilibrium of a body. Ready? Let's get started. I know, the equilibrium of bodies is not a topic of mathematics, but of physics. However, I want to present a method that requires no prior knowledge of physics, neither about forces nor about vectors. Regarding the forces, often covered across several chapters in the textbooks, we'll summarize only the essential information needed to study the equilibrium of bodies. As for vectors, we won't use them explicitly, since this video aims to be short and practical. That said, let's make one thing clear. Having a solid understanding of forces and vector calculus would actually make some steps of the procedure even quicker. There is plenty of great material available online, but if you are interested in a no-panic explanation, let me know in the comments. I'll be happy to start working on dedicated content for that. Before we begin, I'd like to give you a preview of the procedure. In the first step, we will do a roll call of the forces involved by consulting few handy identity cards. We will keep only those whose activation conditions are met by the problem. In the second step, we will use other information on these cards to fill out a table, which will provide us with two key values. In the third step, we will answer two questions using a flowchart to find the correct relationship between the two key values. Once the relation is solved, the problem is due. Well then, let's start by taking a look at the forces, beginning with a few general remarks and then moving on to create their identity cards. Formally, a force is a physical quantity that causes a change in either the speed or the shape of a body. However, this definition can be misleading. There are cases where a body is subject to forces, but doesn't seem to change its speed or shape at all. This happens when the forces cancel each other out, a situation known as the equilibrium of a body, which is exactly what we aim to study in this video. So, how can we tell that a force is acting if we can't see any of its effects? We'll rely on a more practical idea of force. We'll think of a force as a push. If you push against a wall, even if it doesn't move, you are still applying a force. Pushing, pulling, lifting, holding, these are all key actions that reveal the presence of a force. These actions can take many forms, including those that occur at a distance. That's why we'll later get more specific. For each type of force, we'll identify the exact condition that determines its presence. We'll call it trigger condition. But for now, let's focus on two other pieces of information: magnitude and direction. When we push something, we can do so with varying strength, from a light nudge to a maximum effort. As a physical quantity, force has its own unit of measure, symbolized by a capital N called the Newton. And there are instruments designed to measure this magnitude. We won't go into detail, but to give you an idea of how strong 1 Newton is roughly the force needed to lift a kiwi fruit. With 100 newtons, you can lift a small suitcase, and with 1000 newtons, you can lift a motorcycle. Magnitude alone is not enough to describe a force, because the effect of a push also depends on the direction in which the body is pushed. Let me show you what I mean right away. The picture represents two people dragging a round table. Each is applying a force of, let's say, 100 newtons. If they work together, pulling in the same direction, 100 plus 100 equals 200 newtons, and everyone is happy. But what if they pull in opposite directions? It's clear that their efforts cancel each other out, so 100 newtons and 100 newtons add up to 0 newtons. And then there are other cases where the directions are off angle and the sum of the two forces can be 20, 50, 100 or other values. In short, direction is crucial because it affects how forces add up. We want to represent direction numerically, and to do that, we'll follow this approach. First, draw a reference semi-axis, horizontal and extending infinitely from the center of the pushed object to the right. Now take a force and represent it with an arrow showing the direction of the push, making sure the starting points coincide, as shown in the figure. The direction of the force will be the angle alpha between the semi-axis and the force. Alpha is called the direction angle, or argument of the force. If you choose the angle above the semi-axis, more precisely the angle measured counterclockwise from the semi-axis, then we assign the angle a positive sign. If you choose the angle below, which is perfectly fine too, we assign it a negative sign. The ID cards we are going to build contain precisely the trigger condition, the formula for the magnitude f, and the direction angle alpha relative to the reference semi-axis, RS in short. You need 3 cards to get started: the weight force, the spring's restoring force, and applied forces. Later in your studies, you will encounter other forces, but these won't invalidate the method. You'll simply need to create an ID card for that new force and add it to your collection. For the sake of completeness, I'll show you how to do this for a couple of additional forces, but you'll see that by then the process of creating the cards will already be clear. Notice that we won't create ID cards for normal forces and friction, because these belong to the final step of the procedure and will be handled separately. That said, let's begin by creating the ID cards. Let's start with the weight force. This force is present whenever the body we are studying has a mass, unless it is openly irrelevant, and is near a planet due to gravitation. Since almost all exercises take place on Earth, this is one of the most common forces you will encounter in problems. The magnitude of the weight force is the product of the body mass m in kilograms and the planet's gravitational acceleration constant g. For the planet Earth, this constant is 9.81 meters per second square. The constant g represents how much a body's speed increases with each second of freefall. On Earth, a body in freefall increases its speed by 9.81 meters per second every second it falls. The push caused by gravitation is always directed toward the center of the planet, that is downward toward the ground. We can conclude that the direction angle alpha is minus 90 degrees. To make the notation clearer, we make use of images. Here is how an ID card captures the essence of the weight force. Let's set it aside and move on to the next force, the spring's restoring force. This force is present only if the body being studied is in contact with a spring that has been extended or compressed from its original length. The magnitude of this force is the product of K and X, where K is the spring stiffness. Some springs are stiffer and have high K values, while others are softer with lower K values. This constant K is measured in newtons per meter and represents the amount of force in newtons needed to stretch or compress the spring by 1 meter. X is the spring's extension or compression, measured in meters, not the total length of the spring, but just how far it has been stretched or compressed. Regarding direction, remember that spring's restoring force is a pullback force. The spring tries to return to its original length. So we draw the axis along which the spring is aligned and choose the direction of the force as the one that will bring the spring back to its original size. Just recall the sign convention for angles: positive if above the reference axis, negative if below. Applied forces. In many exercises, you will find someone pushing, pulling, lifting, carrying objects, and they can do so in any way they want. So, for all these forces, you won't find formulas for magnitude or direction. The information will be given in the problem description or shown in a picture, like the one you can see in this card. These first 3 types of force are enough to solve the most common problems in equilibrium. Later in your studies, you might come across other types of forces. Let's take a quick look at a couple of them. Archimedes' buoyant force only applies to bodies immersed in a fluid. Its magnitude is the product of d, v and g, where d is the density of the fluid, V is the volume of the part of the body immersed in the fluid, emphasis on only the immersed part, and finally G is the gravitational acceleration, the same one we encountered when talking about weight. The buoyant force acts on the opposite direction to the weight force, so the direction angle alpha is plus 90 degrees. Finally, electrostatic force. This force acts on a body that carries an electric charge when it's near another charged body. The magnitude is calculated using a formula known as Coulomb's law. As for the direction, it's enough to know that the force is aligned along the straight line connected the two charged bodies, and it's attractive if the charges have opposite signs, or repulsive if the charges have the same sign. Now that we have the force ID cards, let's dive into the actual procedure. Step 1. Go through the force ID cards we just reviewed in any order you like. If the trigger condition is met in the problem, that means the force is present, otherwise discard it. For instance, if we are studying a weight attached to a spring, we will keep the two cards at the top. Once you've finished the roll call of all the forces acting on the body, check whether the body is resting on or pressed against a solid surface, like a wall, the floor, and so on. If so, denote by alpha 0 the angle of inclination of that surface relative to the reference axis. You can freely choose either of the two angles formed between the contact surface and the reference semi-axis. If no such surface is present, even better, alpha 0 will be 0. Step 2. Now we complete a two-column table, where each row corresponds to one of the forces involved. In each row we'll write, in the first cell, F times cos alpha minus alpha 0. In the second cell, F times sin alpha minus alpha 0. Here, F is the magnitude of the force, alpha is the direction angle, and alpha 0 is the inclination of the contact surface, if any. Anyone familiar with vector analysis might recognize that these are the vector components. The first column corresponds to the axis parallel to the contact surface, the second to the one perpendicular. Once the table is filled out, sum each column. Call the result from the first column F parallel, and the result from the second column F perpendicular, or F perp, to its friends. Step 3. Here we'll establish whether the body is in equilibrium, meaning whether the total force acting on it is 0. This equilibrium condition, once written and solved, will allow us to extract the final information required by the problem. But to write it correctly, we need to introduce the last two forces that we are missing from our analysis so far, the normal force and the friction. We'll rely on a flowchart to establish how the normal force and the friction force behave in the problem. First, let's ask ourselves, is the body in contact with a solid surface like a wall or the ground? If the answer is no, then the equilibrium condition is twofold, F parallel and F perp are 0. If the answer is yes, move on to a second question. Does the body experience friction with that surface? By experience friction, we mean is at least one force trying to push or pull the body so that it would slide along that surface? If the answer is no, the equilibrium condition is F parallel equal to 0. If the answer is yes, then the condition becomes F parallel less or equal than mu times F perp in absolute value. Here mu is the coefficient of friction, a dimensionless number that depends on the material and the texture of both the body and the surface. At this point, all that remains is to use the data to solve the equilibrium equation. Before doing that, I'd like to take a moment to explain the flowchart. The first question in the flowchart essentially asks whether the trigger condition is met for the normal force. The normal force is a push that a solid surface exerts on a body that tries to penetrate it. When this force is present, its magnitude equals F perp, and its direction points outward, perpendicular to the contact surface. As a result, the body is automatically in equilibrium along the direction perpendicular to the surface. The second question in the flowchart corresponds to checking whether the trigger condition for friction applies. If friction is not present, then equilibrium requires that F parallel is 0. But if friction is present, it acts to brake the body by exerting a force opposing to the direction of the body's movement along the surface. However, friction alone doesn't always guarantee equilibrium, because its intensity can never exceed the product of the friction coefficient μ and the force F_perp. That's why, to ensure equilibrium, the force F parallel, trying to slide the body along the surface without friction, must not exceed the maximum force that friction can sustain, which is μ times F_perp. Summing up the procedure, we have: Step 1. Identify the magnitude F and the argument alpha of each involved force, plus the inclination alpha 0 of the contact surface if present. Step 2. Fill the table with the force data. Then sum each column to get F parallel and F_perp. Step 3. Check the presence of the normal force and the friction to establish which equilibrium condition applies. If no solid surface is present, both F parallel and F_perp must be 0. If a contact surface is present but no friction, then the equilibrium condition becomes F parallel equal to 0. Finally, if friction is present, F parallel must be less or equal to μ times F_perp in absolute value. Now we'll take a problem and see how our method crushes it, freezes it, melts it, and blows it away. A child is lifted by the parents with inclination shown in the figure. The child weighs 20 kilograms and the parents are applying forces of equal magnitude. The goal is to find the magnitude of these forces. Let's solve it. We start by taking attendance of the forces. Weight force, present. The child has mass, so magnitude mg and argument minus 90 degrees. Springs force? No, there are no springs. Applied forces? Yes, 2. The parent on the right applies a force with unknown magnitude F and angle relative to the reference semi-axis of 60 degrees. The parent on the left applies a force with the same magnitude F but angle 120 degrees. Since the child is not in contact with any solid surfaces, alpha 0 is 0. So, for step 2, we have a table with 3 forces. I suggest strengthening your mental math skills by using the numerical data from the problem only at the end. For now, limit the calculations to just cos and sin of the angles. Once this is done, we sum the values obtained in each column to get F parallel equal to 0 and F_perp equal to square root of 3F minus mg. Since there are no contact surfaces, the equilibrium conditions are F parallel equal to 0 and F_perp equal to 0. The first condition is already satisfied. The second gives square root of 3 times F minus mg equal to 0. Among these quantities, the unknown is F. Solving for F and substituting the problem's data, we obtain that each parent's force has a magnitude of 113 newtons, and the problem has been solved. Let's see one more problem. A cart with a mass of 210 kilograms is fixed along a slope inclined at 20 degrees to the horizontal by an elastic rope that behaves like a spring, with a spring stiffness K of 1800 newtons per meter. Neglecting friction, by how much will the elastic rope stretch? The forces present in the step 1 are the weight force, magnitude mg, argument minus 90 degrees, and the restoring force of the rope acting as a spring, magnitude kx, where x is precisely the extension we need to find, and the argument is determined by the restoring direction of the spring. Since the slope is 20 degrees inclined, the argument is 180 minus 20 degrees equal to 160 degrees. No other forces are present. The ground has inclination, so alpha 0 is minus 20 degrees. It is negative because it is descending and the angle is below the reference semi-axis. By applying the formulas for the table in step 2, for both the involved forces, calculating cos and sin, and finally summing down each column, we obtain the expressions for F parallel and F_perp, that you can read and check in the last row of the table. Moreover, the presence of the inclined plane, but absence of friction, as stated in the problem, leads us, in step 3, to the equilibrium condition F parallel equal to 0. This is equivalent to 0.342 mg minus kx equal to 0. We solve for x, obtaining 0.391 meters. So the elastic rope stretches by approximately 39 centimeters. Allow me to ask you one last question. would the exercise change if there were a coefficient of friction μ equal to 0.5 between the ground and the cart? I will leave this problem as an exercise. Try using the procedure to get the equilibrium condition. Most of the previous steps can be used again. However, the mathematical part you will need is a bit more challenging. It is easy to make mistakes, so you need to use your head. The maximum extension of the rope should be 93 centimeters. Mathematically, it could also have negative values, but we will exclude this case because the rope behaves like a spring only when stretched, not compressed. Thank you for your attention. I hope this simplified yet general procedure can support your studies. To help grow the channel, leave a like and share it with anyone you think might be interested. Write in the comments if there are any topics you'd like support with, and in the meantime, don't panic.